In 2007, in his State of the Union address, President Bush spoke of America being addicted to oil. Many scientists and researchers before him have been saying similar things, that our burning of oil threatens our national security and our burning of coal threatens our future of humanity. Thankfully, we've now moved from arguing about whether there is a problem to talking about how to fix the problem. The elephant in the room is nuclear power. Opponents say that nuclear can supply us with hundreds or thousands of years of carbon-free domestically produced power, and detractors point out that the waste, safety, and cost issues of existing nuclear power plants are big problems. So many of these points depend on the particular characteristics of the pressurized water reactors that are in use today. But pressurized water reactors aren't the only kind of reactor possible. Back in the 1950s, before the first man had gone into space, researchers at Oak Ridge National Labs built one and later a second molten salt reactor. These reactors are very different from, and some would say much more promising than, the pressurized water reactors that were later commercialized. The workers at Oak Ridge were very excited about their work, and just after orders for the second generation of commercial pressurized water reactors began to start, work on the molten salt reactor was canceled. You might ask, why? Our speaker today, Dr. David LeBlanc, started working on nuclear fusion in the 1980s. His work on fusion led to an interest in molten salts, and that led to the story of the molten salt reactor. Since then, he's changed his focus to redeveloping the molten salt reactor, and he'll be discussing what happened 4 decades ago and why molten salt reactor designs today can be better than they were back then. David.
All right. Thank you very much, Ian. Okay, I have a lot to talk to you about today. I'm going to go fairly fast, but hopefully give you a lot of information, pique your interest to learn more, so to speak. I'm with the physics department at Carleton University up in Ottawa, but I've also started a company, Ottawa Valley Research Associates, to try to expand some of the things I've been working on and filing patents, etc. First question is, can nuclear help solve our climate change problems, energy problems, etc.? The nuclear industry presently would be more than happy with building about 400 reactors over the next 30 years or so. That's about all they could really handle, realistically. That merely keeps the status quo of sort of replacing reactors that are shutting down, the ones that are 60, 70 years old kind of thing. We need thousands of large reactors to truly make a difference. So is there a way existing or next generation? There is a lot of designs out there people have been trying to promote for decades now. Can these other designs realistically accomplish this? Now, when you're thinking about reactor designs, it's important to quantify all the priorities, and I can sort of list 7 here. Overall power cost, definitely, of course, and that should be broken into capital cost, which is often quite expensive, and then your fuel plus operating maintenance is usually a lot more reasonable. Overall safety, definitely job 1, so to speak. We have to do as much possible in that area. Resource utilization is an area that there's dramatic difference in different reactor designs, and you have to break that into 2 categories as well. The quantity and quality of the starting load, how much fissile material you need to start your reactor, and what types can you use. Can you use low enriched uranium? Can you use spent fuel? Some reactors can use plutonium from spent fuel, but not all the other nasty actinides. I'll be showing the molten salt reactors, or liquid fluoride reactors as they're also known, can use those. And then there's also the annual requirements. Proliferation resistance, an extremely important concept, and that as well is important to break into sort of 2 areas. Subversion to a state program. Is a country perhaps going to take over the technology and use it in nefarious ways, so to speak? And then also more of an individual thing, or theft or terrorist takeover. Can terrorists steal significant quantities of material? Then there's also long-term waste, radiotoxicity. That's a very important concept, and there can be very big differences in different reactors. How much R&D is required for a new design or getting a design up to code? And then what is the capability for rapid deployment? We need a lot of reactors. What can we do for that? So the existing reactors, light water reactors, pressurized water reactors, boiling water reactors, and CANDUs, overall costs, they're very high, but arguably competitive with coal. The safety is good through expensive engineered sort of defense in depth. Resource utilization is modest for startup. They're not too hard to start up, but they're very poor annually. And you need a lot of uranium dug out of the ground to support these. proliferation resistance is good through all the international safeguards we've set up. Long-term waste, very poor, especially the once-through cycle, which is the most economic and widely used. Very, very poor, sending a lot of radiotoxicity to waste. Even if they do use what's called plutonium recycle, that doesn't really improve things dramatically. R&D, that's one area they benefit. There's very little that is required. Capability for rapid deployment, it's just not there. Even on labor alone, we just couldn't get too many build programs going to really get enough of what we need. What about gas-cooled pebble bed reactors? This is an area that is seeing more advance in recent years, and it is an interesting system. There's cost savings possible, but there's no real great reduction in overall complexity. They require a massive pressure vessel, and that really limits the size of the core and the power. So almost the same size pressure vessel as a pressurized water reactor for maybe a quarter of the power or even less than that. The rad waste production is very similar to light water reactors, and also you've got radioactive graphite. It's not too horrible of stuff, but you've got that as an added bonus. The reprocessing of fuel in this design is extremely difficult, and that's part of the reason they say they're more proliferation resistance, but that means the uranium utilization is even worse outlook. From a safety outlook, they are excellent in decay heat management. They can get rid of decay heat quite readily, but that's only sort of half the equation in reactor safety. The other half is criticality events, etc. And they're quite good on this, as any reactor is by engineered systems, but that is still a possible issue. And I have an asterisk here, and I've got some little extra comments down below. There's more for people reading the slides later here. And one of the asterisks here is the reverse is true for accelerated driven systems, where you're keeping things subcritical by supplying neutrons from accelerator. Yes, we can instantly shut that down. It helps a lot in criticality, but it does nothing for you in helping in decay heat management. What about the other Generation IV reactors? Generation IV, just briefly here, was a program set up in around 2002, a worldwide program to try to investigate what are the reactors we should be working towards in the long term. Pebble bed reactors was one of those. Another is supercritical water. It's operating water at a much higher temperature than they're using now. It really only gives you modest improvements, gives the thermal efficiency up a bit. But extremely challenging corrosion issues to solve there. Sodium cooled fast breeder reactors, they've been around for a long time, a few smaller ones or demonstrations built. In general, most would agree they're more costly and higher safety concerns. We can make pretty much any reactor safe to the public as long as we have a nice containment vessel around it. But many would argue, not all, but many would argue that more likely to have accidents with these type reactors. They need a massive amount of fissile material to start, 12 tons of fissile material, plutonium, etc., to start these up. And the doubling time is how long it takes if you breed fuel, meaning you're making more than you're consuming. It would take 40 years on these designs to make enough for the next plant, so to speak. Lead-cooled fast breeder reactors, there's some possible savings there. They save an intermediate loop, etc. But they require even more fissile material. So I have an asterisk down here that with that, like the entire plutonium supply of the U.S. weapons program, spent fuel, etc., that would only be enough for 30 or 40 reactors, so it really limits how fast we can develop these. Gas-cooled fast breeders, that's one of the other Gen 4 reactors. That has a lot of the similar issues here. Now, what about thorium? We keep hearing about that. Thorium is more and more in the news, more and more in the conversation of the nuclear industry. Thorium is fertile on its own, but it can produce a fissile element, uranium-233, which is a really good nuclear fuel. It has numerous advantages, works well in any spectrum. We don't have to have a fast spectrum, or we don't slow the neutrons down, like the uranium-plutonium cycle. However, any use in solid fuels, involves very difficult fuel processing, okay? There's a lot of inherent radioactivity in things. It's very difficult to reprocess. But what about fluid fuels? And what about the Generation IV reactor that was made for thorium? And that is the liquid fluoride reactor. It's over 50 years old, but it's never really looked any better. And historically, this is called a molten salt reactor. I'll probably be switching a bit between terms here. the older term is molten salt reactor, but liquid fluoride or liquid fluoride thorium reactor, a lifter, is a term that's becoming more used. So liquid fluoride, molten salt overview. What did the original program at Oak Ridge end up with, and what factors guide design, how did design evolve, why was it cut off, what's happened since then, and do new priorities and new ideas, do they change the outlook of things? So looking at what's called a traditional molten salt breeder reactor, this is a figure right out of the Generation IV program. Molten salt contains the fuel itself, and the fissile and the fertile material flows through a critical core that has graphite logs here that flows between the logs, in and out of that core, and it's only critical inside the core, so heat is generated in here, but that hot fluid comes out and goes through an intermediate heat exchanger. That secondary coolant salt then drives either a gas cycle or a steam cycle. Originally it was a steam cycle, but we feel that a gas Brayton cycle would be much more useful now. We show control rods here, but I'll talk a little bit later. You don't really need control rods in these type of reactors. We can process out fission products, okay, to be able to be a breeder, or as I'll show in a few minutes, about a break-even breeder. We can also dump these salts to emergency dump tanks very easily, either by valves. Well, by valves if we wish, and if we do nothing else, we have what's called freeze plugs that will melt if the salt starts to get hotter than we want, and drain to the tanks that are set up to deal with the decay heat. When you shut a reactor down, that doesn't turn off all the power. There's so much radioactivity going on that there's a lot of power being generated, and we have to deal with that. That was a 3 Mile Island event. They didn't have, the reactor was shut down, but they had to deal with that decay heat. So the general attributes of this sort of traditional design, it's called a molten salt. You have a salt that sort of dissolves, or there's a mixture of in this case, the fertile thorium fluoride and uranium fluoride mixed in a carrier salt that's lithium fluoride and beryllium fluoride. And that lithium has to be isotopically enriched, which makes it a little expensive, but not too bad. It has a nice high outlet temperature of 700 degrees, so we have a nice high thermal efficiency. Oak Ridge work was over 44% on the steam Rankine cycle. If we switch to a gas Brayton cycle, like a helium or even supercritical carbon dioxide, we can get up to the high 40s. The fission products in this case were moved on a 20-day cycle. Some were moved a little quicker, some a little slower, and I'll talk in a minute about how a lot of them come out automatically. Now, protactinium here, protactinium is sort of the intermediate between thorium and uranium-233. Thorium becomes protactinium-233, and that will decay to the thing we want, uranium-233, in a 27-day half-life. We often need to remove that, or in this case, we need to remove that for this design, which is a bit of a problem here. You want to take it out of the neutron flux so it doesn't take another neutron and not get to what you want. And I'll talk more about that a little bit later. It has a very low fissile inventory. We talked before about like 12 tons, 20 tons. This is only 1.5 tons or 1,500 kilograms for a typical gigawatt or 1,000 megawatt size plant. Has a breeding ratio of 1.06, which is modest compared to the fast breeder reactor, but you don't need to breed much fuel to start your next reactor. So that means the fuel you burn in a year, which is about 800 to 1,000 kilograms, you sort of end up with 6% more than that at the end of the year. That gave a 20-year doubling time, which back when it was in competition with fast breeder reactors was not as good as the fast breeders, but we had to change the fast breeders later for safety reasons, and they're nowhere near as good as 20 years anymore. General benefits of any molten salt design: volatile fission products, gaseous fission products, things that want to come out of the salt will come out as we're operating, and we simply collect them. The most important thing is xenon. It's a gas that really just loves to absorb neutrons. We really want to get rid of that. It's quite radioactive, so we can remove that. It just comes out of the salt. We assist that by bubbling helium through the gas. So if everything that wants to come out of the salt we take out continuously and store safely off plant or away from the reactor, if there is any kind of major spill, etc., it just solidifies. There's really nothing that wants to come out of there. So it's really hard to imagine ways that we can really spread any radioactivity around. The salts have a very high boiling point, and we operate them at low pressure. There's no pressure vessels here whatsoever. It's just a big tank, basically. Any temperature increase instantly lowers the reactivity. That's a very good safety feature. The fuel salt's at the lowest pressure of the circuit. That's sort of the reverse of a pressurized water reactor, where every stage the things are trying to get to the outside world, whereas in this, the radioactive salts are at the lowest pressure of the circuit. We don't need control rods or burnable poisons, etc. There's almost no excess reactivity. There's no danger of accidentally pulling out control rods. There's none in there to begin with. And we have that simple freeze plug that melts upon overheating, and it just drains things. So lots of inherent safety features here. So the general benefits: inherent passive safety, low fissile inventory, very high thermal efficiency, and they're ideal for light water reactor. TRU is transuranic waste. We can get rid of the more nasty aspects of those, which I'll show in just a second. They're a perfect system for that. It's very hard to get rid of those transuranic waste in other designs. And when we have the ability to use the closed thorium cycle, just very briefly, thorium becomes U-233, and U-233, when it fissions, can give a little bit more than 2 neutrons per fission. And if we don't waste too many of those neutrons, one of those neutrons, or at least one, can go to making another U-233. And if exactly one goes, we sort of break even, and we're creating as much fuel as we're burning, so to speak. Thorium is dirt cheap. It's very extremely plentiful. So if we can close the cycle here, we get down to about 800 kilograms a year. That's maybe like $40,000, $50,000 worth of thorium for a plant that's going to be generating revenues of maybe $500 million a year worth of electricity. So it's just a drop in the bucket. The transuranic waste in general are produced at a much lower rate, and it's much easier for us to just keep burning those off within the reactor, so we get a much, much lower long-term radiotoxicity. That's what I want to talk about for a minute now here. This graph is from a researcher in France that shows the radiotoxicity, and radiotoxicity is a little different than just radioactivity, because if we're putting things away, if they get into the groundwater, some forms of radiation are a lot worse if you ingest them, compared to if they're just sort of sitting around or you get them on your clothes, etc. So radiotoxicity is the important thing. What this shows, this dashed line here, is showing the fission products themselves. And the vast majority of these have pretty short half-lives. This is a logarithmic scale on both sides, so going up by a factor of 10 every time here, and in time we're going up by a factor of 10 every time. So over the first few hundred years, those fission products drop off dramatically. Initially, they're the most radiotoxic part of the waste, but after 500 years or so, they're quite low. Now this level right about up here, 10 to the 6 or so, that's the radiotoxicity of the uranium you'd need to fire up a pressurized water reactor. So if we can get lower than that, that's a good benchmark to aim for. But the pressurized water reactor, what's really radiotoxic is the higher actinides, things above uranium, neptunium, plutonium especially, americium, curium, etc. Those, a pressurized water reactor will be throwing away like 200, 300, 400 kilograms of those per year. That is what's so long-term radiotoxic. This green line is showing what we can get with a molten salt reactor or liquid fluoride. We're not producing much. We only have maybe 10, 20 kilograms in the salt at any time. So when we reprocess, we put that back in. Now, anytime you sort of process things, you have to assume that you might lose a tiny bit. And 0.1% loss is a very conventional rule of thumb for losing things to waste, okay? But since we're only processing kilograms per year, we get a very low radiotoxicity. Whereas a fast breeder reactor, even with the same loss rate, they're processing tons sort of thing per year. They will not be that great. Now, they hope that they can do even better than 0.1. In practice, especially sort of the more famous integral fast reactor, they've probably never really done much better than 1%. They hope they can do a lot better than that. But they're starting with a lot more radiotoxic actinide waste to begin with. So it just shows that with a molten salt reactor that we put the plutonium, et cetera, back in the reactor to keep burning off, we're turning the waste problem into more of a 500-year problem than really a million-year problem. And we can engineer things that are going to be not leaking for 500 years quite easily, as opposed to trusting that we can do that for millions of years. Now, proliferation resistance, that's a very important question, and a lot of people are going to have different opinions on this, but it's an extremely important one to talk about. Now on the pure thorium to U-233 cycle, there is a lot of proliferation resistance built in here already. There's always going to be a lot of an isotope called uranium-232. It's got a moderately long half-life, so it's going to stick around, but it gives you a really strong gamma ray from one of its daughter products. That's really hard to shield. It really makes it very easy if someone's trying to smuggle it around, very easy to detect. You can't really shield that out. It's such a high energy gamma ray. Makes illicit use extremely difficult and highly detectable. There's been never any national program based on making weapons out of U-233, even though yes, it technically is possible. And it would also be extremely hard to imagine how you could steal from reactors that the salt's never less than, say, 500 degrees Celsius kind of thing. A colleague of mine, Kirk Sorensen, also made a great suggestion here that if you're using the pure cycle in a molten salt reactor, liquid fluoride reactor, we can instantly denature that, okay? Uranium-235 or 233, they're both materials that can be used in a weapon, but if they're mixed with enough uranium-238, natural sort of uranium, they can't be made into a weapon. So we could keep uranium-238 as a fluoride sort of in standby, and if anything goes wrong, inspectors lose contact with the reactor, that can very quickly be dumped into the salt, makes it useless for weapons, and you can't really start up the reactor again. Now, protactinium removal can lead to clean uranium-233. So if we can, we really should try to avoid this. Because if it's becoming U-233 just from this storage of protactinium, it doesn't have this U-232 or very, very little of it. So that's an important point. There's only very small amounts of plutonium in this cycle, and it's extremely poor quality. You could really never make a weapon out of it. Now, we can also denature these cycles, and that means we run them with enough U-238. We still want to be majority relying on the thorium part of things, but we put in enough U-238 so that any uranium that you can take out, you couldn't really use to make a weapon. Because the pure cycle does represent what people call highly enriched uranium. For a lot of people, as soon as you say that word, to them it's a no-go. So running the denatured cycle includes having enough 238, and it does mean there's more plutonium present because that U-238 can start becoming plutonium by absorbing neutrons. But it's still a very poor quality, and plutonium is a lot more difficult to remove from the salts than uranium is. And in many designs, it will affect your conversion ratio. Conversion ratio and breeding ratio are sort of the same things. It's how much per fission you're sort of making more fuel. So looking at the quality of produced plutonium, weapons grade is almost all Pu-239. Reactor grade is only about 60% that. And one of the basic things that really gives you a lot of protection here is Pu-238 generates a massive amount of heat because it's got a fairly short half-life. In a reactor grade, it's 1.3%. It would make it very, very difficult, but not impossible to make a weapon out of reactor grade. For a denatured molten salt cycle, and this is what's from what we call a 30-year once-through converter design, which I'll talk a lot more about later. It has massive amounts of this Pu-238, so, and a lot less 239, et cetera. Technically, it would be still something that would need to be guarded, but probably next to impossible to make a weapon. On the pure cycle, you do have the 233, but the plutonium is basically absolutely worthless. It's almost all 238. The thing would probably melt if you tried to put enough together to make a weapon. Now, some problems specific to the molten salt, the single fluid, where you mix the thorium and uranium in the same fluid, graphite moderated design. They had a fairly high power density, and graphite has a limited density depending on your power output, or power density, sort of, sorry. So it has a lifetime of 4 years. We have to replace that graphite every 4 years. The fuel processing is hindered by the chemical similarity of thorium and the most important rare earth fission products to remove, which are the rare earth fission products. And there was also a problem with the temperature reactivity coefficient that was sort of recently discovered. Quite simple to work around and no problem with some of the ideas I'm going to talk to you about today. And protactinium separation, it does add that unique proliferation concern, which we'd like to get rid of if possible. Some design basics, two fluid versus single fluid. Single fluid is sort of what we call the traditional, but for most of the Oak Ridge program, they were trying to do what's called two fluid design, where you have a separate fuel salt that contains the uranium-233, maybe a little bit of thorium, but by definition the two fluid has none, and then a blanket salt that contains the thorium, and that's sort of going to catch the neutrons and convert the fuel for you. The advantage of that is when there's no thorium in the fuel salt, it makes it much, much easier to process for the fission products. PA removal is not really necessary, and there's an asterisk here, I'll basically quickly describe that. How many neutrons you lose to protactinium is based on your sort of power density, okay, your neutron flux. The thorium, though, is sitting in a much lower neutron flux, or we can just have a lot more of this blanket salt, and effectively it dilutes it, so we lose a lot less, and there is really no need for any protactinium separation, and it's a pretty complex thing to do. It has a very strongly negative temperature and void coefficient for the fuel salt, which is also very good. And then there's also converter designs, or what we'd call once-through designs, where we're basically just having a mix of low-enriched uranium, so uranium that can't be used to make a weapon, and thorium in a single fluid. There's no need for any processing of the fuel salt whatsoever for the entire life of the plant. We're not able to break even. We have to dig up out of the ground some more uranium every year, but much, much, much less than other conventional type reactors. Just basically on design basics here, choice of neutron spectrum, a harder spectrum, a faster spectrum, because we can modify this almost as much as we like. The losses to fission products will drop, so we can maybe leave them in a lot longer. Prompt neutron lifetime is shorter, and that's a bit of an issue on control, etc. And it typically requires a higher fissile load, more fissile material to start these up. Softer spectrum is basically the reverse. We can get that fissile inventory really low. The losses to the fission products, though, are going to be higher, so we might need to remove them quicker. We can't really have any extra structural material. Most designs don't have any at all. It's just graphite and the salts, and graphite's very good with neutron absorption. And the prompt neutron lifetime is much increased, so things can sort of happen slower here. Fuel processing basics, fluoride volatility, it's a process that removes uranium from the salt. It's a very simple process. Fission product removal, it's essential if we want to have a breeder or break-even design, but even for break-even, we can go to several years. Some French studies have gone up to studies showing up to 20 years before removing fission products. Protactinium removal and hold-up, it's essential for single fluid designs that wish to break even, but not really for others. Fluoride volatility, just very quickly, we simply bubble through fluorine gas through the carrier salt, and it converts UF4, which is a solid, well, it's dissolved in the salt, to gaseous UF6 that we can convert back later. Okay, it's an old process that we've known about since the 50s. Fission product removal, sort of historically here, in the early part of the program from 50s to early 60s, they didn't really have any one method that they thought was going to be great. They proposed very many, but none yet proven to be practical. There was a big breakthrough in 1964 called vacuum distillation. It's a very simple system. You just take, every day, take a little bit of the salt away, put it in basically a still. The fission products itself give enough heat to keep it really hot, and the carrier salt will evaporate away. Now, before you put it there, you take any uranium out, then evaporate out the carrier salt, recombine those, the fissile U-233 and the carrier salt, put them back in the core. And that gets rid of most of your fission products, and especially your rare earth fission products. The problem with that is if there's thorium in that salt, it's going to stay with the fission products. So it was really only viewed for a two-fluid design. Later, though, in 1968, they developed something called liquid bismuth reductive extraction. I won't get into details of this, but it does have the ability to process the four fission products with thorium in the salt. But thorium is so chemically similar to the rare earth fission products, it really makes the process very delicate, and they really have to do things at many stages, etc., to do things properly. So it's a complex and costly system, but it does work for single fluid designs. So fuel processing summary here. For two fluid design, we've got all kinds of choices. We can use vacuum distillation. We can use something called salt replacement I won't get into. We can use the liquid bismuth extraction, much more simplified, one stage, because we're not worried about that thorium. And we can skip protactinium removal altogether because it's in that lower neutron flux blanket. For single fluid designs, you're sort of stuck with that one method, and it's really hard not to get into that protactinium removal. If we have converter designs, though, basically what we call burner designs, We've got no fuel processing whatsoever, just simple chemistry control. Now looking at the evolution here, it's crucial to remember that they have very different design priorities in the early days. Long-term radioactive waste, proliferation resistance wasn't really part of their mandate. They didn't have too much concerns there. They really thought back in the 50s and 60s, early 60s, that we have very little uranium in the world, we're going to run out quick, so we have to get these breeder reactors going and breed enough fuel to expand the fleet. They thought they'd have thousands of reactors worldwide by now. That means short doubling time, how long it takes to breed enough fuel for your next reactor. That was a very top priority. And we were in the molten salt reactor program was in competition with sodium-cooled fast breeders. And back then they thought they had a really good doubling time. They don't now anymore for safety reasons. So looking at the program, the strange beginning of this was an aircraft reactor. They didn't make anything that flew like this, but just as the Navy was sort of the birth of the light water reactor, the pressurized water reactor, that was the best thing that fit in a submarine, they thought that a molten salt reactor would be a great way to have a bomber that would be able to fly around for months on end. Replacing a reactor for the heat of combustion, so you don't have any jet fuel on board. Extremely challenging project, to say the least. It did lead to a very interesting test reactor built in the 50s, very high temperature operation, 860 degrees. It had beryllium oxide as a moderator, sort of canned in material here. It had a different carrier salt, sodium zirconium fluoride. It pointed the way to possible power reactors, though, even if the idea was probably quite far-fetched, in my view at least. Now, what I call the rise and fall of the two-fluid reactor. Two-fluid was the focus for most of Oak Ridge's program, and in the late 50s they looked at what we call homogeneous designs, no graphite or anything, just the salt itself. They looked at both converter designs and breeder designs. Now, the carrier salt does provide a significant amount of moderation, slowing those neutrons down, so we can actually play around with the spectrum quite readily. And all these studies were spherical geometry, and they always had a wall, a Hastelloy end. I haven't mentioned Hastelloy yet. It's a high nickel alloy that works really well with these molten salts. It has good corrosion behavior, etc. It's always been in the plan to use these metals like for heat exchangers for the vessels, etc. It would have a vessel wall, and let me just show you a picture here. So it's a very simple design they were looking at in the 50s. Just an inner fuel salt here, which was either just uranium-233 in the fuel salt or more likely some thorium as well, and surrounded by a blanket salt. Very ingenious, simple design. This wall, though, will be in an intense neutron flux, and we know now that it probably wouldn't have too long a lifetime. Maybe we can improve the alloy so it would, but nonetheless, a very, very nice little design. But in the early 60s, though, they proved that we could use graphite with these systems, and that can lower the fissile inventory, and so there was a switch in focus. Okay, we're going to go to graphite moderation, but we still want that two-fluid design because it's so much easier on processing the fission products. Now, the simplest way you might imagine building this is a central core that just has the fuel salt surrounded by a core that has the blanket salt. The problem with that, though, is the critical radius of that inner core would just be too small. It would be on the order of about a meter with the concentrations of fissile that we would put on these salts. That's just too small, not enough volume to have a power-producing volume. So Oak Ridge's solution was, well, we're going to have to mix these salts, not together, but have two salts in the core separated by plumbing, graphite plumbing. Now, that intermixing of fuel and blanket salts done by graphite plumbing, it does give you the ability to have large core diameters and adequate power production, but that graphite, when it's under neutron radiation, first shrinks a little bit and then starts expanding. And that's changing the ratio of the blanket salt and the fuel salt. It's just giving all kinds of problems. And that plumbing was so complicated as well, any sort of one crack would basically mean replacing the whole core. Very hard problem. This just sort of quickly shows some of the engineering specs of showing this. Fuel salt moving up and down a tube here, and blanket salt sort of getting in between the cracks of these tubes. Very difficult. Now, also in the 1960s, they had the molten salt reactor experiment, a very successful test reactor. Small power, 8 megawatts thermal. It was chosen to be single fluid for simplicity. They never really even put any thorium in these reactors. They just wanted to test principles here. Graphite moderation ran in the early 60s. Very successful operation. They would switch around different fuels, U-233, 235, and plutonium. They have found some issues with that hastelloy, that high nickel alloy metal. One with a certain fission product that was sort of getting into the grain boundaries, and another with neutrons can make helium inside the metal, and that helium gets to grain boundaries and gives you problems. But later on, they worked with alloys and not 100%, but mostly resolved those issues later, and we could definitely do more now. Now, 1968 is what I call the start of the single fluid area. That new extraction method, even though they knew it was going to be quite complex and quite expensive, not as expensive as solid fuel processing, it works with thorium in the salt. The two fluid concept was abandoned, and that plumbing problem was left unsolved. And then pretty soon after that, major funding for the molten salt breeder reactor program was canceled, and the R&D extremely limited until quite recently. And this two fluid concept largely forgotten. Now, why was the program canceled? This was obviously going to be speculation. There's a lot of reasons here. First off, what did Oak Ridge do right? First off, they looked to go to the thorium-uranium cycle instead of uranium-plutonium. That's the fast breeder cycle. There's no need for a fast spectrum, a lot less radiotoxicity, etc., a lot more resources of thorium. They brought all the top mines together in one place. Fast breeders and a lot of the other designs were working sort of piecemeal, some at Argonne, some other places. Everyone was together in Oak Ridge working to this. It really reinforces all the efforts. And they kept reactor safety at the forefront. There's inherent safety features of these as opposed to engineering safety. In Oak Ridge, they had a lot of voices in the early safety about we have to really be worried about events of low probability. What did Oak Ridge do wrong? Well, it turns out it's a lot of the same things. They decided to focus on the thorium cycle, but in the 50s to the 70s, production of plutonium for the military was a top priority for the government as well, and by extension, the Atomic Energy Control, which controlled reactor development. They brought all the top mines together in the same place. That meant that all around the country, elsewhere, Argonne, everywhere else, they really knew very, very little of the molten salt program, and government relies on the opinions of experts from around the country. Reactor safety kept at the forefront. Alvin Weinberg was the director at Oak Ridge, the inventor of the pressurized water reactor, actually, and he really caused raised the ire of AEC's infamous Milton Shaw by raising safety concerns about pressurized water reactors. And soon after that, he was fired as director and the program canceled. So not necessarily that those two are directly related, but most people feel it is. What's happened since then? Well, in the late 70s, Oak Ridge still kept things going with almost no funding, so not really any good engineering work being done, things being built, etc. They started to focus more on denatured designs where you'd have U-238 in there, either converters or break even. They showed, even surprised themselves, that you could break even with a design that had U-238 present, so the uranium was useless for weapons. There's been little funding, but there's been many vocal advocates worldwide, but without getting much funding, doing things on their own. Until it was chosen one of the 6 Generation IV reactors back in 2002. That's really sparked a lot of interest. And probably the biggest work being done for the last 5 years at least has been in France. There's a large group there really doing great work on modeling, chemistry, etc. They found a reactivity problem with the early 70s design. I'll just briefly explain that. You do get the temperature coefficient is the needed negative term instantly, but as the graphite sort of lags behind and warms up in temperature, if the reactor is starting to get hotter, the graphite eventually brings that coefficient to be positive, which is a problem we need to fix, and what I'm going to talk about in the future, definitely we can fix that. They look to decrease the processing needs. They realized how difficult that liquid bismuth extraction is by allowing the breeding ratio to drop down to break even. And they have moved towards a harder spectrum that doesn't have graphite in the core itself. And they've also added a blanket salt around, just radially around. There's been more US-based efforts, but a lot of the focus has changed from molten salt reactors to what they call molten salt cooled reactors, traditional solid fueled reactors based on the TRISO fuel. That's where you have the fuel inside little tiny beads that are inside pebbles or inside prismatic fuel elements, but using molten salts without any fuel in them, but as clean carrier salts. And a lot of those people hope that that effort can lead to pretty good reactors now, and then eventually to more ideal molten salt fueled reactors. But it has sort of taken away some of the interest here. And in those designs, the real big challenge is making sure that you don't have what's called a positive void coefficient. They can do that, but it's a really hard, really big challenge. There's also been much work worldwide on using these systems to get rid of transuranic waste, take away that plutonium and neptunium, et cetera, from light water reactor spent fuel and burn it up in these reactors. Now the French design, just very quickly, this is what they've evolved to. It's just a very simple core of fuel salt here surrounded by a radial blanket. Some of the engineering details they haven't gone into too much of how they're going to have a barrier and things like that. A reflector on top and bottom. You can't have just pure graphite here. It would give too big of a power spike. So I think they're still working on what kind of material that's going to be, the reflector. Very simple design. It would be quite difficult to try to build in a axial reflector as well. So it really, because it's not a completely encompassing blanket, that really does limit their potential a great deal. A lot of good Russian work. And they're working mainly on a system that just burns transuranic waste. So there's no thorium, uranium, or anything in that reactor. They just keep feeding in waste transuranics from spent fuel, and it's just a simple big tank of salt. We protect the outer vessel. That outer vessel, we don't want it to see too many neutrons, so they'll put like a graphite reflector here and even some steel to limit how many neutrons get to that outer vessel. And they've been doing great work. Updating priorities, if we're trying to look ahead to what we should be doing, what we could be doing. Fissile material for starting up, mainly because they need so little and we can use a lot of different types. We can use transuranic waste, whereas light water reactors, they can't put everything in, only plutonium. And they can't just run on plutonium either. They need uranium there as well. So it's not, we don't really need to breed fuel. Proliferation resistance and long-term waste reduction, that's a much higher priority now. And we should really try to minimize the need for fuel processing and its complexity. Ideally, remove it altogether if we can. But there's no two experts or two nations that are really going to agree on ranking all these different priorities and how different reactors fit into those priorities. So it's probably very good if we go forward on multiple options. There's a lot of flexibility in these designs. And keeping in mind a few design concepts here, keep it simple, stupid. A lot of people trying to think of new designs. Idea people are often drawn to very complex solutions, but any new improvement in the nuclear field can be monumentally expensive. So we really have to choose our battles, make sure any changes we're making are relevant, needed, and easy to verify. Off the shelf where possible. There's a lot of good examples to this. There is a lot of advantages to going to a gas cycle to get the final energy out of these, but there's a lot of R&D involved in trying to match a gas turbine to what your reactor is. So a lot of people are still saying, well, we'll just still stick to the steam cycle. So there's a lot of cases like that. Another aspect is we have a certain temperature we can reach with the metals that we work with, about 700 degrees Celsius. If we stick to that, we sort of know our limitations. There is some advantages to going higher, but then it opens up all these things that we'd have to verify, et cetera. And also an expression hopefully most of you understand, rice bowl breaking. Whenever you're talking about a brand new idea, you're going against people that it's affecting their livelihood, breaking their rice bowl. You've got to keep that in mind. And be aware of that and minimize if possible. A good example is if we're going to the pure thorium cycle, we're basically removing uranium from the industry, and that's a pretty established industry. Just to keep that in mind, but maybe if we can do just as good with the uranium, keep that in mind. And also remember that there's a lot of existing corporate players, et cetera, that have models in place. We're going to be going against those, or maybe we should bringing in those players because they're not doing too well with their designs. So some new ideas for your consideration that I've been working on and patenting, et cetera. One is reviving the two-fluid concept. That's the main thing I want to talk about. Another is what I call a barrier-free design and a possible fuel processing-free design. So not as important an aspect or a little bit more theoretical, but something I haven't sort of made public yet, so it's a sort of public disclosure here. And then simplified converter design, starting with what Oak Ridge came up with and trying to expand on that. So getting into the two-fluid ideas first, restating the two-fluid plumbing problem, a sphere within sphere, like fuel salt with graphite or without, surrounded by blanket salt, that's the simplest approach. But that if there's no thorium in that inner fuel salt, the critical radius is just too small. It makes your reactor too small, not enough volume to get enough power. So it's too small for power plants. The standard conclusion is, well, we have to find some way to interlace those two fluids. So what's my solution that I've come up with? First, starting with a hint, you can ignore the math here, but what's called the buckling ratio just shows that if you have different geometries, if you have a sphere or a cylinder, long or short, etc., slab geometry, if you have the same materials in place, you'll have different critical radius. And it turns out that if you have the same materials in a sphere compared to a long cylinder, the long cylinder, its diameter will be about 77% of the critical radius of a sphere. But the thing with a cylinder, a long cylinder, we can get as much power producing volume as we want. So just showing things very generalized here is what I'm looking at is elongated cylindrical geometry, okay? Our core is the necessary pretty small diameter, about 1 meter. So this can be as simple as just a pipe carrying the fuel salt, or it might have graphite elements in here as well if we choose to do that, surrounded by a blanket salt. So about half the neutrons, actually a little more than half the neutrons, will leak out of there into the blanket salt, be converted into uranium-233, which we can quite easily transfer into the fuel salt, okay? At the end, we can crimp down this inner pipe. That makes it sort of subcritical here, okay? And any neutrons, any last neutrons that are emitted can still get out into this blanket. So in this very, very simple design, we can have almost no neutron leakage. And that fully encompassing blanket is really important for allowing you to do all kinds of useful design changes here. You know, the new concept's advantages, we can use the simple two-fluid fuel processing without that plumbing problem that plagued Oak Ridge for so long. It has very strongly negative fuel salt coefficients, which are great, and Oak Ridge always liked those. The blanket salt should also be slightly negative, and Oak Ridge's design actually had a blanket salt coefficient that was slightly positive, because if it heated up, some of it was leaving the core. In this case, there's none in the core itself, just around, and it acts as a bit as a reflector, so when that gets less dense, less neutrons will be reflected back, and it can slow things down as well. Very simple designs to build, to transport, etc. Ease of modeling and prototyping. These are so simple we can probably model them in 2 dimensions almost. And very low fissile inventory. The two-fluid design of Oak Ridge already was lower. It was about 700 kilograms, but they were wasting a lot in sort of what we call plenum spaces at the top and bottom. We could easily get this down to about 400 kilograms per gigawatt electrical, or even lower. So showing a cross-section of graphite-free, meaning we don't have any solid moderator. It's basically just a pipe within a pipe, and sometimes the people have used the term tube within shell, which is a heat exchanger term. Now we do need a barrier between the two, like Oak Ridge often had. That could be hastelloy perhaps. Molybdenum is a great material neutronically and for radiation damage, but really hard to work with. Or maybe just simple carbon composites or silicon carbide, etc. A lot of choices here. Just to show some numbers, and I can sort of back these up, I do a lot of data mining, okay? Taking studies that were done by Oak Ridge or the French or the Russians, et cetera, or Japanese are doing a lot, Czechs, et cetera. In their studies, Oak Ridge studies for 122 centimeter diameter sphere with 0.16% fissile concentration, that should be able to reach break even long term. If we extend that to long cylinder geometry, that shrinks down a bit to just under a meter in diameter. And if you put in the basic power densities, actually these are quite conservative numbers, 200 kilowatts per liter, fairly slow salt speed, 2 meters per second, typical inlet and outlet pressures. A 6.6 meter long core, that gives you over 400 megawatts electrical just there. Now and there's also other ways that give you larger diameters. And that would be for the same length, more power. Now other variations, if we allow that concentration to rise a little bit, we end up with more excess neutrons to deal with, so we can start thinking, well, we could put a metal barrier in there, molybdenum or even stainless steel. We can start thinking about alternate carrier salts that are a little less expensive, etc. And it gives us even greater simplification of fission product processing because we can leave them in a lot longer. We have more spare neutrons. And just like the French work has shown, going to 20 years or beyond that for removing fission products. This just quickly shows another variation that's part of my patent that we might have sort of a calandrial arrangement where you have a central tube that's easily removable. Gives you a gap in between as well that you can really quickly detect any kind of leak. I'll also quickly mention, we always, just like Oak Ridge always proposed, you run your blanket salt at a little bit higher pressure. So if there's any crack or leak, just blanket salt goes inwards and it just shuts down your reaction. The critical issue though is this core blanket barrier, this barrier between the two, and that's something we'd have to verify. But we benefit from the fact that there's a lot of work in the fusion field that has a lot more funding using these same salts as a coolant, and they have that first wall that is the most hostile environment you can possibly imagine. So they've been looking at a lot of materials with both the salts and a high neutron flux, molybdenum, silicon carbide composites, or even just simple carbon composites. They're leading candidates. And one important thing to mention is they have to have systems that are completely impermeable. We do not care if gases leak through these because both the blanket and fuel are making a little bit of xenon, etc. So we don't need impermeable as long as there's not liquids really leaking through. Now, Hastelloy and stainless steel are shown to be possible if we lower the temperatures a bit. And that's not really too big of an issue. It is a bit hard to make sure we have salts that have a low enough melting point. But if you lower the temperature a bit, we can really start to consider using stainless steels or the Hastelloy. And ease of retubing means, well, even if your barrier doesn't last forever, it's not going to be that expensive to fix. And just quickly, this is just showing some work from Steve Zinkel at Oak Ridge that's looking at different materials in the fusion field where you have that very intense radioactive field. And a lot of materials have sort of a window of operation. And you can see how stainless steel's 316 stainless steel here. It's only really verified up to about 550 degrees. So if we lower our operating temperatures a bit, we might consider using those. Silicon carbide are sort of in an ideal region as well. So we have a lot of choices. Now graphite cores, adding graphite in there has some advantage. It's going to lower the it's going to have a similar diameter actually, but it does lower the power density because it's not all salt. It's only about 10 to 15% salt then. But I just want to show an embodiment, an idea that has no real barrier material in a neutron flux, because that's what we know the metals can survive outside in contact with the salts, but it's the neutron flux. So one of the ideas I've been looking at is having a simple system here where it's our typical sort of hexagons of graphite with central fuel channels here. And this is just sort of a graphite sleeve, something to hold all those hexagons together here, and surrounded as usual by a blanket salt. But how do we get to the outside world? That's where things are a little more interesting. What we do here is, if those graphite elements are, say, 15, 20 centimeters wide, we constrict those down. So now fuel blanket salt can get between those pipes, okay? And that basically kills criticality, and it'll absorb all those neutrons. So where we contact from graphite to Hastelloy, which Oak Ridge looked at this before, brazing to the tubes, that's done outside the flux, okay? So it does, you might be saying, oh, well, that's back to the plumbing problems. But we have no blanket salt between those pipes. So we don't care if they're expanding and contracting. It's not really going to change the overall criticality of things or the overall ratio of things. So just one of the suggestions here. Now moving on beyond this two fluid, if the barrier does prove a possible stumbling block, what other options do we have and still try to break even here? And looking at a barrier-free, fuel processing free. So can we run break even without a barrier and even without fuel processing? Now harder spectrum does allow you to leave fission products in a lot longer, so maybe we can get up to the 20, 30, 40 year range. Now, excuse me, as well, the other thing we have to keep in mind is that outer vessel has to be protected against a high neutron flux. And a common solution, if we're talking about a tank of salt idea here, is putting a graphite reflector. Okay, that sort of protects things. But it's a very surprising result that can actually start to increase the neutron leakage, because what happens is you get sort of a much bigger increase in power at the outer edge. And I'll just show you a quick graph here showing the power density with or without a reflector. If you don't have a reflector, the power density at your outer edge is really low, so hopefully the graphite could last a very long time. But as soon as you put the graphite in there, it reflects back the neutrons, it flattens out this power density, which is great for if you have graphite in the core. We don't care about this if it's just a pure salt. But that makes a lot of power, so we have to have a thicker graphite, and you end up losing a lot of neutrons just in there. So what have I come up with? It's the idea, we have a very simple sort of tank of salt here. We have a graphite liner, but in that graphite liner we embed a lot of thorium. Very simply, we don't have to use the complex solid fuel methods here, just thorium carbide or even thorium itself in the graphite. And that thorium is going to absorb a lot of neutrons, and basically it's not a reflector anymore. It's absorbing those neutrons. Now, just like the Russian work has shown with graphite reflectors in Oak Ridge as well, we usually put a little bit of cooling channels in that graphite just to keep it cooler temperatures. But in that design, what I sort of call a liner equal to blanket, the core salt is a single fluid, potentially denatured with U-238, especially in the harder spectrum. 238 doesn't hurt you as much. So in the early years of operation, the liner is almost completely absorbing. That means, oh, you're losing neutrons, but we don't have very many fission products yet, so the neutron budget should still be fine. Now, as fissile U-233 and or plutonium start to build up in that blanket, it's going to start making more fissions there, which will increase the power a bit, and also start reflecting back more neutrons, which is what we need because we're having more fission products to absorb neutrons in the salt. So ideally, we could make this liner that's permanent. We don't have to replace that, or at least last, say, 20, 30 years and have a midlife refurbishment here. And also, hopefully, without any fuel processing whatsoever. Now, this is a very early stage, requires a lot of modeling, it's quite speculative. The graphite lifetime and the ability to get rid of fuel processing definitely goes up with the core diameter. If you make this absolutely enormous, it will definitely work. Because the flux at the wall goes down with power density. So if you have a really big one, that's low power density. But the question is what diameter would be needed to give you the full 30 years or more in the graphite and be able to forego fission product processing. If it's too large, that just might mean too much fissile material needed to start these up. The third thing I want to talk to you, the final thing I want to talk to you is what's called converter reactors or denatured molten salt reactors. The starting premise of this is of Oak Ridge is what they call the 30-year one-through design, and this is from a report called ORNL TM 7207, and I really should mention there's a massive amount of data out there for people to learn on their own through the Oak Ridge Library or also through the website Thorium Energy that has dozens and dozens, if not hundreds, of different documents available for people to download, discussion groups. You can train yourself, talk to other people, learn things, contribute, etc. Very important. But getting back to this work, it was a 1,000 megawatt output. It was started up on low enriched uranium, so as long as you're less than 20% U-235 with thorium, no salt processing whatsoever, just some simple chemistry control. It wasn't a breeder, but you just add small amounts of low enriched uranium manually. Low power density, so the graphite would last full 30 years. Similar startup fissile inventory to a light water reactor. And averaged a conversion ratio, which is sort of the other term for breeding ratio. We use conversion when it's less than 1, of 0.8. Now, looking at the lifetime needs, it only needed about 1,800 tons of uranium lifetime. That's less than a third of what a light water reactor would need, and much better than even a CANDU, which has advantages over light water reactor. And at the end of the 30 years, it's very simple to remove that uranium. So we just remove that uranium and recycle maybe in the next reactor. That lifetime ore drops down to 1,000 tons, which is getting really, really good here. The transuranics, Oak Ridge didn't really have too much concern back then. We really should recycle those. They're harder to remove, but we can do this one time only, bring as many inspectors as we want in, bring the equipment in for 3-6 months, process out all those transuranics, put them in the next core as well. And if we do that and assume the typical 0.1% losses, you're only talking losing a kilogram of transuranics to waste in 30 years. And that's as good or even better than the pure cycle where we're processing every few months, 6 months, or a couple of years kind of thing. So it's a very exciting design. What are some suggested improvements looking at not modern technology or modern priorities? We might look at graphite pebbles, a pebble bed where the pebbles are just graphite, very, very simple and cheap. That removes the need for what's called flux flattening. You don't want any part of the reactor too high power or the graphite doesn't last long. Pebbles can be moved in and out. So we can go to higher power densities if we like, because we can move those pebbles in and out very simply. And we can even put some pyrolytic coatings on that graphite quite simply for increased safety. Higher power density, smaller cores, we can make, let's say we make the core half the size. Well, the graphite's going to only last 15 years, but you're using the same over the long period, same amount of graphite. So that really lowers your starting fissile inventory and your starting capital cost just at the cost of adding or replacing every 15 years too. There's advantages to using elongated cylindrical geometry. It eases fabrication and dealing with what's called axial plenums. And there is tricks to limit neutron leakage that Oak Ridge came up with in these single fluid designs. Going to graphite-free, getting rid of the graphite, going to just a simple tank of salt here. We can retain, if we want a softer spectrum, we just go to lower fissile concentration and let that salt itself moderate the neutrons. So we can do a lot of things in that design. What's also quite exciting for me is looking at alternate carrier salts. The traditional carrier salt called FLiBe, fluorium, well, based on fluorium, lithium, and beryllium, etc. There's problems with that. The beryllium's a bit toxic. It produces tritium, which is really a pain to deal with, not impossible, but we have to catch that tritium, make sure it doesn't get out, because tritium can sort of move through metal walls if they're hot enough, etc. So we can switch to perhaps sodium beryllium fluoride. It was always sort of Oak Ridge's second choice here. Very low cost, low melting point, so we might be able to lower the melting point enough. We can start thinking about using stainless steel throughout. Nickel alloys are fairly expensive, so if we could go with simple stainless steels, that might save a lot of money, etc. Another one that's not as well known is sodium and rubidium fluoride, along with uranium and thorium, of course. It's really low cost and no tritium production at all. Beryllium and lithium are the things that can make tritium for you. If we get rid of those, that can really simplify things. A lot of people have been telling me, though, with the gas cycle, we have a lot less to worry about with the tritium leakage, etc. And then probably the most exciting is just sodium fluoride. Dirt cheap. It does have a bit of a higher melting point though, so we were sort of pushing the limits here, but a lot of advantages there. And surprisingly, when you really look at the numbers, and there's been a lot of different studies on this, you don't really lose all that many more neutrons. Even though lithium and beryllium are considered to be really excellent, sodium not so much, you really only maybe double or maybe triple how many neutrons you're losing to the alternate carrier salts. And sort of looking at this graph-wise here, if you look at how much uranium is used for a light water reactor, or even when you add in uranium and plutonium recycle, things are not that much better for the light water reactor. I throw in a sodium-cooled fast breeder reactor here. They don't really start up on uranium, but that's sort of how many tons you'd need just to start up if you were taking that out of uranium-235. The converter reactor, only 1,800 tons or 1,000 tons if we do just one uranium recycle. And if we allow the carrier salts, even if they're alternate salts that with triple the losses, we're still only rising things a little bit, and that's where it's most impressive. So you're only annually needing about 35 tons of uranium a year, or maybe 47 tons if we have an alternate carrier salt. Now, typically the price of uranium fluctuates a lot, but $50 per kilogram is a rough guide here. So for the converting reactions, it's only $1.5 million a year, really a drop in the bucket of overall, only going up to $2 million a year for alternate salts. And even if you imagine a 100-fold increase in the price of uranium, you're still only talking $150 million a year for fuel, which is only 2 cents a kilowatt hour. So we could imagine, well, all these potential resources of uranium if we allow the price to rise that much. So this does really get down to the argument of peak uranium. Just like peak oil, people think, well, maybe we're actually running out of uranium, especially if we try to get designs that are a lot more reactors using this. And it also the sustainability of uranium mining, which a lot of people don't think is the nicest thing in the world. But as shown though, we can, even with an enormous price increase, there's a little effect on the fuel cost for the denatured molten salt converter reactor. And we can also view that as a first step. We can add fuel processing later if uranium does prove to be scarce or we don't like the uranium mining. So some conclusions here. Molten salt designs have inherent safety features that favor overall cost, waste reduction, low cost, and rapid deployment. They also have great flexibility to match different priorities, and mainly on proliferation concerns. We can change these in ways that make them just absolutely so much better than anything out there now. So they can change to meet priorities. We can run these on minute amounts of thorium or more modest amounts of uranium, but at the advantage of utmost simplicity. Now, what way forward? It is very difficult to attract corporate interest on designs like this. Was back in the 70s, will be now. corporations would have no lucrative fuel fabrication contracts that they can sort of plan on making money for years on end. Starting any kind of new design or something that hasn't been built to commercial size yet, it's sort of a minimum, maybe about a 15-year return on investment, which is a hard sell to shareholders. And the existing nuclear players have sort of their choices in place. But as I said before, they're not doing too well with those, so maybe we can sort of change some of their minds. Oops. Other corporate players, big oil. They're making massive profits, but they're more and more agreeing with people about the concept of peak oil. Maybe we are going to, within 30, within 50, within 100 years, run out of this. Maybe at the price of some of their profits now, they can still be the big players in the energy field by investing in these concepts now. Also the chemical giants. A majority of the work on these is chemical in nature. They're more chemical plants than nuclear, so they would have an ideal sort of skill set for fitting in this. Individuals with deep pockets, the people like Gates and Branson, Allens and Buffetts, etc., they're looking for ways to invest in the future. What better way than something like this? We need to get the ball rolling, and that's really the difficult part. Now, I really think international cooperation here is key to spread the cost and also spread the rewards. The ITER model, ITER was the International Thermonuclear Experimental Reactor, really showed a way for different countries to work together on something that was expensive but very important. So maybe that is a rough guide, but with a lot more corporate involvement. This is quite speculative, of course, though. And there's likely no one design that's going to be best for everyone or all nations or all utilities. So it's really best to move forward on several different designs, and even things like molten salt cooled reactors. A lot of their potential research and development is going to be applicable to everyone. And there's nothing like competition to yield the best results. So what's needed in the short term, a lot of things, a lot of neutronic modeling, a lot is being done, but we need a lot more done. A lot of fuel chemistry work and corrosion studies on various carrier salts and the materials for heat exchangers, etc., and potential materials for a barrier. There's a lot of non-nuclear component testing that we can do today, pumps, valves, heat exchangers, etc. And all these things just need minor levels of funding to get going. We need sort of the expression of dime one to get going, and then maybe it'll be a lot more easier for people to get funding. Researchers around the world would love to work on these. The more people I talk to, they would love to work on it, but there's just no real funding stream available now. We need to get that going, and that really is the hardest part of all. And that's what I'd like to talk to you about today, so open for any questions now. Well, it depends on your rate. Oak Ridge often had like all these time frames. Well, if we want to get this out in 30 years, they're always quite conservative there. Not spending that much money, like over 30 years, spending only $1 billion or $2 billion, those numbers are a bit dated. It boils down to manpower and money. The more we can get in, the faster things can go. It depends on the complication level we're looking at. If we're looking to build really simple converter designs, they're basically identical to what Oak Ridge built as a test reactor, so we could maybe save a lot of time in there. You need just a little bit of money to get things going, to really get a good program going, tens of millions or hundreds of millions a year to really move at a fast pace. Questions? All right. Well, I hope you wish to learn more on your own. There's lots of information out there for you too. Okay. So thank you.